Welcome to Lucid Mind Chemistry channel. I'm Majid and in today's video I'll be solving O-Levels Alternative to Practical Paper 42 from October-November 2020. You can go to any specific question by following timestamps given in the video description. Let's start solving. Question number 1. A student investigates two different aqueous electrolytes using the apparatus shown. So we have two aqueous electrolytes present in this solution. We have carbon anode, carbon cathode, and in the external circuit we have a battery attached. Complete the table. If aqueous electrolyte is dilute sulfuric acid, then you have to mention the name of product at anode and observation of that product. So for dilute sulfuric acid, we know that the ions present are H+ aqueous and OH negative aqueous from water. We also have H+ aqueous from dilute sulfuric acid and sulfate -2 from dilute sulfuric acid. As anode is positive, so negative ions will move towards anode, so it could be OH negative and sulfate. As we know that sulfate does not discharge, so only OH negative will make the product. As we know that OH negative ions move towards anode and they lose electrons to form water along with oxygen and 4 electrons. So oxygen is the product that is formed at the anode. So we can write the name of product as oxygen. And the observation for oxygen gas is that bubbles will be produced which are colorless, as oxygen gas is colorless. So we can write bubbles of colorless gas. Similarly, for reaction at cathode, we have negative electrodes, so H+ ions will move towards cathode and it will form hydrogen gas, for which the observation is bubbles of colorless gas. Second aqueous electrolyte given is aqueous copper 2 sulfate. So for aqueous copper 2 sulfate, again we have H+ and OH negative from water. And from copper 2 sulfate we have copper +2 aqueous and sulfate -2 aqueous. So again, as we know that sulfate ions are not discharged, so it is OH negative which will move towards anode to form oxygen. The reaction will be same as given previously, so we can write oxygen is formed. The observation is given, bubbles of colorless gas. Now for cathode, we know that these two are positive ions, so this will move towards cathode. Among these two, Cu+2 is below in discharge series as compared to H+ ions, so Cu+2 will be discharged while H+ ions will not be discharged. The equation will be like this: copper +2 aqueous will move towards cathode, it will gain electrons to form copper solid. So the name of product is copper and the color of copper is pink solid. You can also write brown or orange color. Part B, state the test and its observation to identify hydrogen gas. Now the test is that we can place light at splint. And the observation is that it will extinguish with a pop sound. Question 2. When solid group 1 nitrates are heated, they decompose and give off a gas. the gas relights a glowing splint. Name the gas that relights a glowing splint. Now you should know that nitrates upon decomposition produce oxygen gas, and it is the oxygen gas that relights a glowing splint. So we can write oxygen. A student investigates the rate of decomposition of 4 group 1 nitrates. The student heats each of the nitrates separately with the Bunsen burner. The student measures the time taken for a glowing splint to relight for each nitrate. This is metal nitrate and it is heated. So what happens? Oxygen gas is formed and then glowing splint is put in the test tube. The time taken for the glowing splint to relight is measured. Part B, it is important to control the amount of heat supplied by the Bunsen burner. Suggest 2 ways the amount of heat supplied is kept constant. Now the heat supplied could be kept constant by keeping the distance between the flame and test tube constant. Also the intensity or the height of flame can also change the results. So we can write same size of flame, or you can also write same height of flame. Second is the intensity or the heat that is supplied by the flame, so we can write same strength or same intensity of flame. You can also write that the amount of gas supplied should be same for each flame. Part C suggests a variable involving the metal nitrate that should be controlled. As we are decomposing the nitrate, so the decomposition depends on particle size of the nitrate or the surface area. It also depends on the amount or number of moles of metal nitrate. As greater the amount, more oxygen will be produced and faster will be the rate of reaction. So we can write same amount, or you can write same number of moles of metal nitrate. You can also write same surface area. Or particle size of metal nitrate, as all of these affect the rate of chemical reaction. Part D, each experiment is repeated 2 more times. The results are shown in the table. We have metal nitrate, lithium, potassium, rubidium and sodium nitrate. This is experiment 1, this is 2, this is 3, and these are the time taken for glowing splint to relight in seconds. And this is for average time. Number 1, use the times in the table to calculate an average time for each metal nitrate. Do not use any anomalous times. Write your answers in the table. Now for lithium nitrate, we can see that in experiment 1 we had 100 seconds, in experiment 2 we had 150 seconds, while in experiment 3 we had 100 seconds. So the closer values are 100 and 100, and 150 is not taken as it is anomalous. So we can find the average 100 plus 100, as there are 2 values, so divide by 2 and it equals 100. So the average time for first experiment is 100 seconds. Similarly for potassium nitrate, in experiment 1 we have 150, in 2 we have 300 and 320. So these two are closer together and this is anomalous time. So the average will be 300 plus 320 divided by 2, which equals 310. So we can write 310 seconds. For rubidium nitrate, the values are 400, 450 and 410, as these two are closer and this one is anomalous. So the average will be 400 plus 410 divided by 2, which equals 405. So we can write 405 seconds. For sodium nitrate, we have 200 seconds in experiment 1, 200 in experiment 2. So these two are same. While in experiment 3, it is 240, which is anomalous. So 200 plus 200 divided by 2 will be equal to 200 seconds. So we can write 200 for the last experiment. Part 2. Which metal nitrate decomposes the fastest? Use information from the table to explain your answer. As we can see that the average time taken by lithium nitrate was 100, while for others more time was taken. So less time means that the reaction was fastest for lithium nitrate. So we can write lithium nitrate. And the explanation is that from the table we know that it took the least time. So we can write average time is smallest for lithium nitrate. Question number 3. A student is provided with a solution K, which is aqueous sodium hydroxide. The student determines the concentration of K by titration. The student measures 25 cm³ of K and transfers it to apparatus A. This is the apparatus A. So in A we have aqueous sodium hydroxide. Part A. Name a piece of apparatus used to measure 25 cm³ accurately. Now for measuring 25 cm³ we can use two different apparatus. One is pipette, as pipette is very accurate to measure 25 cm³. You can also use another apparatus, that is burette. It is also accurate to measure 25.0 cm³. Part B. Name apparatus A. Now we can see that this is apparatus A and the name is volumetric flask, or you can write graduated flask or standard flask. So it could be volumetric flask, or you can also write standard flask or graduated flask. The student makes up the 25 cm³ sample of K, which was sodium hydroxide, to 500 cm³ with distilled water. This is solution L. So now the solution L is aqueous sodium hydroxide, which is 500 cm³. The student transfers 25 cm³ of L into a conical flask and adds 2 drops of methyl orange indicator. So as L is sodium hydroxide aqueous, so methyl orange is added in aqueous sodium hydroxide. Solution M is 0.0500 mole per decimeter cube sulfuric acid. This is the other solution. M is put into a burette. So it is aqueous sulfuric acid that is put in burette and run into a conical flask until the indicator changes color and the end point is reached. Part C. Why is it wrong to wash out the burette with distilled water immediately before filling it with M? Now as we can see that M is sulfuric acid and this is the concentration. So if distilled water is used immediately before filling with M, so what will happen that it will dilute M by reducing the concentration. So we can write it dilutes the acid, or you can also write that it decreases the concentration. Part D, what is the color change of methyl orange indicator at the endpoint? As we know that methyl orange was put into sodium hydroxide, so the color of methyl orange in base is yellow. While from the burate acid was put, so we can say that the methyl orange in acid is red in color. So the color changes from yellow to red. You can also write orange or pink. Part E, the student does 3 titrations. The diagram shows parts of the burate with the liquid levels at the beginning and at the end of each titration. This is titration 1, 2 and 3. Choose the diagrams to complete the table. Now you should remember 2 things. One is that you should always take the reading from top to bottom for burate. And second is that this is initial and this is final. Similarly, the first one is initial, the second one is final. So in titration 1, the initial reading is at 0, so we can write 0.0 for first reading. In the final burate, we can see that it is 23.1, 2, 3, 4, 5, 6, 7. So 23.7 as final burate reading. Similarly, for titration 2, the initial reading is 10.1, 8. And the final reading is 34.1, 2, 3, 9. So initial is 10.8 while final is 34.9. For third titration, initial is 20.1, 20.2 and final is 44.1, 2, 3, 4 and 5. So initial is 20.2, final is 44.5. Now volume of M can be obtained by subtracting these 2 readings. So 23.7 minus 0.0, we have 23.7. 34.9 minus 10.8, now the value is 24.1. Similarly, subtracting 44.5 with 20.2, the reading is 24.3. Next is the best titration results. So the values that are closer together will be the best titration results. First is 23.7, second is 24.1 and then we have 24.3. So as these two are close together, so these will be the best titration results. Summary: take the best titration results in the table. We have already done that. Use the ticked results to calculate the average volume of M. As we have two values, one is 24.1, second is 24.3. So divided by 2. The average comes equal to 24.2 centimeter cube. Part F. Solution M is 0.0500 mole per decimeter cube sulfuric acid. Calculate the number of moles of sulfuric acid in the average volume of M used in the titration. This is the concentration in mole per decimeter cube. We have to find the number of moles. And this is the volume that is given. By using the formula, number of moles is equal to concentration in mole per decimeter cube into volume in decimeter cube. So we can put the values. Concentration is 0.0500. Volume is 24.2 centimeter cube. So we can convert it into decimeter cube by dividing by 1000. So the moles come equal to 0.00121 moles. Part G. Dilute sulfuric acid reacts with aqueous sodium hydroxide as shown. we have sulfuric acid and it reacts with 2 moles of sodium hydroxide to form salt and water. Calculate the number of moles of NaOH in 25 cm³ of L. From balanced equation we can write H2SO4 ratio NaOH. Now the number of moles from balanced equation is 1:2. So we can write 1:2. And the number of moles obtained previously was 0.00121 for H2SO4. So we can write 0.00121. And for sodium hydroxide we can find the number of moles. So it will be X by cross multiplying. X equals 0.00121 multiplied by 2. So the number of moles of sodium hydroxide come equal to 0.00242 moles. Now this is the moles of sodium hydroxide in 25 cm³ volume. Part H. Calculate the number of moles of sodium hydroxide in 500 cm³ of L. As we already know that 25 cm³ of L consists of this much number of moles, so we can write volume ratio moles. So for 25 cm³ of L we have 0.00242 moles. So for 500 cm³ of L we would have X number of moles of sodium hydroxide. So by cross multiplying, X equals 500 into 0.00242 divided by 25. So the number of moles of sodium hydroxide comes equal to 0.0484 moles. Now this is the number of moles of sodium hydroxide in 500 cm³ of L. Part I. Calculate the number of moles of sodium hydroxide in 25 cm³ of K. Going back to the question, we can see that 25 cm³ of K is used to make solution L, which is 500 cm³ of L. So it means that the number of moles in 25 cm³ of K is equal to the number of moles in 500 cm³ of solution L. This is because on dilution the number of moles does not change. So the number of moles in 25 cm³ of K will be the same as the number of moles in 500 cm³ of L. So we can write 0.0484 moles. Part J. Calculate the concentration of NaOH in K. Give answer to 3 significant figures. The formula of concentration is equal to number of moles divided by volume in decimeter cube. So as the number of moles are given, which is 0.0484, divided by the volume that is also given 25 cm³. So 25 cm³ can be changed into decimeter cube by dividing by 1000. So the value is 0.025 decimeter cube. Now dividing these two, concentration comes equal to 1.94 mole per decimeter cube. K. Between each titration, the student washes the conical flask with water. A second student repeats the experiment but uses L instead of water to wash the conical flask. Now we know that L is a solution of aqueous sodium hydroxide. State and explain whether the second student titration volume of dilute sulfuric acid would be smaller, larger, or unchanged compared with the first student's volume of dilute sulfuric acid. As the first student washes the conical flask with water, so by washing with water the number of moles does not change. While the second student washes with sodium hydroxide aqueous instead of water, so it means that it will change the number of moles of sodium hydroxide. So as number of moles of sodium hydroxide are increased, so the volume of sulfuric acid would be larger, as more acid will be required to neutralize sodium hydroxide. So we can write volume of dilute sulfuric acid will be larger, as we have more alkali in flask. You can also write more L is present in flask. Question 4. You are provided with a mixture of copper 2 carbonate and carbon. Both copper 2 carbonate and carbon are solids. They are both insoluble in water. Copper 2 carbonate reacts with dilute sulfuric acid and forms an aqueous solution. Carbon does not react with or dissolve in aqueous dilute sulfuric acid. In the diagram, they have given a mixture of copper 2 carbonate and carbon in this, and this one is dilute sulfuric acid. Use this information to plan an experiment to produce a sample of pure carbon from mixture. You are provided with a mixture of copper 2 carbonate and carbon as well as dilute sulfuric acid, both are given in the diagram, and distilled water. You have to access the apparatus normally found in school chemistry laboratory. No other chemicals are available. Your plan should include details of how to separate the carbon and purify the carbon. Now we can see that we have a mixture of two different substances. One is copper carbonate and second is carbon, and we have dilute sulfuric acid. Now copper carbonate does react with dilute sulfuric acid while carbon does not react. So what are we gonna do? First we will add dilute sulfuric acid to this mixture and then stir or shake the mixture, or you can also heat until all of the copper carbonate has reacted with dilute sulfuric acid. And we know that when copper carbonate reacts with dilute sulfuric acid, it forms carbon dioxide gas. The carbon is present in insoluble form, so it can be separated by filtration. In the last, we can wash the carbon and obtain pure carbon from the mixture. So first point will be to add acid to mixture. And stir, or you can also write shake or warm the mixture. Now this will be continued until all of copper carbonate has reacted. And what we are seeing are the bubbles of carbon dioxide gas produced. So we can write until bubbling of gas stops. Or you can also write that until acid is in excess. Now carbon is left and copper carbonate has reacted. So we can write the third point as to filter off the carbon. Because carbon is insoluble. Fourth point will be to obtain pure carbon, so we can wash residue of carbon with distilled water and dry it. Now by this method we can obtain pure carbon from this mixture. Question 5. A solid mixture R contains 2 cations and 1 anion. The table shows the test that a student does on R. Complete the table. Identify any gases that are formed in the tests. First is R is dissolved in water. The solution is divided into 3 portions for test. One is B, C and D. And observation is that a colored solution is formed. Now we know that transition elements are actually those that form colored compounds. So we can write that R contains ions of transition element. B part 1. To a portion of the solution from A, aqueous ammonia is added until a change is seen. And the conclusion is that R contains chromium+3 or iron+2 ions. Now we know that both chromium+3 and iron+2 form green precipitate with aqueous ammonia. So in the observation section we can write green precipitate is formed. Part 2. An excess of aqueous ammonia is added to the mixture from B part 1. And conclusion is that R contains chromium+3 or iron+2 ions. Now you should know that both of the precipitate formed from chromium+3 and iron+2 are insoluble in excess. So we can write the observation: precipitate is insoluble in excess. C part 1. To a portion of solution from A, aqueous sodium hydroxide is added until a change is seen. And conclusion is that R contains chromium+3 or iron+2 ions. Again, from the cation identification table, you should remember that both of these positive ions form green precipitate with aqueous sodium hydroxide. So we can write the observation: green precipitate is formed. Part 2. An excess of aqueous sodium hydroxide is added to the mixture from C part 1, and conclusion is that R contains chromium+3 ions. Now out of chromium+3 and iron+2 precipitate formed, iron+2 precipitate is insoluble in excess, while the precipitate of chromium+3 is soluble in excess aqueous sodium hydroxide. So from this conclusion we can write that precipitate dissolves in excess. And as this is of 2 marks, so the second point will be it forms green solution. Now C part 3, the mixture from C part 2 is warmed and the gas formed is tested with damp red litmus paper. The gas turns damp red litmus paper blue. From this observation we can conclude that the gas formed is basic in nature. Now this test is for ammonium ion, so we can write ammonium ion is present. And as it is of 2 marks, so for gas we can write ammonia gas is formed. Part D, R contains sulfate ions. This is the conclusion. So part D is the test for sulfate -2. Now you should know that for sulfate ions test we add barium nitrate along with nitric acid. And what happens is that barium nitrate will form barium sulfate, which is insoluble white solid. So in the test we can write aqueous barium nitrate is added along with dilute nitric acid and the observation would be that white precipitate is formed. This white precipitate is actually barium sulfate. So the anion confirmed is sulfate, while the cation present were 2. One is ammonium ion and second is chromium +3. So among the 2 cations we had ammonium and chromium +3, and one anion was sulfate. Question number 6. A student investigates the temperature rise when different masses of magnesium are added to dilute hydrochloric acid. In each experiment, the student pours 100 cm³ of dilute hydrochloric acid into a beaker. Second is places a thermometer into the acid. Third is records the temperature of the acid. Fourth point is he adds a known mass of magnesium to the acid and stirs the mixture. And last point is records the highest temperature reached. This is the diagram. Magnesium is being poured into the solution of 100 cm³ hydrochloric acid and the student uses thermometer. A. Part 1. The temperature rise with each mass of magnesium is less than expected. Give one reason for this. As we can see that this beaker is open, so we can conclude that heat is lost to the surroundings. Or you can also write that heat is transferred to the beaker, because beaker also gets hot when the temperature rises. Part 2. State 2 changes that can be made to the apparatus so that the temperature rise for each mass of magnesium is closer to the expected value for each mass. Again, as the heat was lost to the surroundings, so we can cover the apparatus or we can use the lid. Or you can also write that we can use closed container instead of an open container. Second thing is that instead of beaker you can use polystyrene cup or insulating material. The diagram shows parts of the thermometer stem giving the highest temperature recorded using different masses of magnesium. Use the thermometer readings to complete the following table. Let's look at the readings. For first, we have 0.20 grams of magnesium and the temperature is 25, 25.1, 25.2. For second thermometer, we have 0.30 grams of magnesium used, and the temperature is 27.5, 6, 7, 8 and 9. Similarly, for the third one, 0.40 grams of magnesium is used, and the temperature increases up to 30.5.6. For the last one, 0.50 grams of magnesium is used, and temperature recorded is 32.1, 2, 3 and 4. Let's put the values in the table. For 0.20 grams of magnesium, the highest temperature recorded was 25.2. Similarly, for second reading of 0.30, the temperature recorded was 27.9. For third one, the temperature was 30.6. And for the fourth one, the temperature recorded was 32.4. Now we can find the temperature rise by subtracting highest temperature with the initial temperature. So 22.6 minus 20.0 comes 2.6. Similarly, 25.2 minus 20.0 comes 5.2. 27.9 minus 20.0 is 7.9. 30.6 minus 20.0 is 10.6. 32.4 minus 20.0 is 12.4. Part C. What evidence in the table shows that the reaction is exothermic? As we can see that for all the experiments, the temperature has risen from the initial temperature. So it means that energy is released, so therefore the reaction is exothermic. So we can write the evidence from the table is that the temperature rises. Part D. Plot the temperature rise against the mass of magnesium on the grid. Draw a straight line through first 4 points. Draw another straight line through the last 3 points. Extend both straight lines so that they cross. Let's do all of these. This is the graph. On x-axis we have mass of magnesium in grams. On y-axis we have temperature rise in degree centigrade. Now from the table, the first mass was 0.10 grams of magnesium and temperature rise was 2.6 degree centigrade. Now on y-axis, each small box is equal to 0.2 degree centigrade. So we can see that here 3.0 comes. So this is the point for 2.6 degree centigrade. Similarly, second reading for 0.20 grams of magnesium from the table is 5.2 degrees centigrade rise in temperature. So the point comes on this place. For the third one, the temperature rise was 7.9. So it will come in between the boxes. Similarly, for 0.4 grams, the temperature rise is 10.6. So the value comes at this point. For 0.5 grams, it was 12.4. So this is the point. For 0.6, again the value is 12.4. For 0.7, again it is 12.4. Now let's draw a straight line through first 4 points. Now we can see that the line has been drawn through first 4 points. And it has also been extended a little bit. Now second line has also been drawn through these 3 points and it has been extended. Part E. Use your graph to answer the questions. In each case, assume that magnesium is added to 100 cm³ of dilute hydrochloric acid at 20 degrees centigrade. Number 1. What is the temperature rise when 0.35 grams of magnesium is used? Now we can obtain this value from graph. This is the graph and we have this point as 0.35 grams. So it comes at this point. And the temperature rise is about this much, which is 9.2 degrees centigrade. So we can write 9.2 degrees centigrade. Part 2. What is the highest temperature when 0.15 grams of magnesium is used? Again, from graph we can see this is 0.15 grams. And if we extend this line, it comes in between this. So this is the point obtained, and on y-axis the value will be 3.9 degrees centigrade rise. So as we can see that initial temperature was 20.0 degrees centigrade, and from the graph we have obtained a value of 3.9. So the highest temperature will be 23.9 degrees centigrade. Part 3. What mass of magnesium is used to give the highest temperature of 26 degrees centigrade? Again, this is the same question. Initial temperature is 20.0 degrees centigrade. So in order to obtain 26, we need 6 degrees centigrade rise from graph. So let's find the mass of magnesium from graph for 6 degrees centigrade. This is 6 degree temperature rise, and this is the point that is obtained. On y-axis, it comes equal to this value, which is 0.23 grams. So we can write the mass of magnesium as 0.23 grams. Part 4. What is the minimum mass of magnesium that reacts with all of the dilute hydrochloric acid? From the graph we can see that the line extends and it goes on until it reaches this point. So this is the junction, and we can see that at this point all of the HCl has reacted with magnesium because the line now becomes straight and no more temperature rise is seen. So let's find the mass for this point. So from the graph it comes equal to this point, which is 0.47 grams. So we can write that the minimum mass of magnesium is 0.47 grams. Part F1. Use your answer to E Part 4 to calculate the number of moles of magnesium that reacts with 100 cm³ of dilute hydrochloric acid. Atomic mass is given. It is 24 for magnesium. Now using the formula, moles is equal to mass in grams divided by molecular mass, or atomic mass in this case. So mass in grams from E Part 4 is 0.47 grams for magnesium divided by atomic mass, which is 24. So the number of moles is equal to 0.0196 moles. Part 2. Magnesium reacts with dilute hydrochloric acid. This is the equation. 1 mole of magnesium reacts with 2 moles of HCl. Calculate the concentration in mole per decimeter cube of the hydrochloric acid. Let's first find the number of moles of HCl that are used. So we have magnesium ratio HCl. From the balanced equation we can see that 1 mole of magnesium requires 2 moles of HCl. So 0.0196 moles of magnesium will require X moles of HCl. Let's cross multiply and find the value of X. We have 0.0392 moles of HCl. Now second part is to calculate the concentration in mole per decimeter cube. The formula of concentration is equal to number of moles divided by volume in decimeter cube. Number of moles is 0.0392 for HCl. Let's find the volume. In the question we have seen that 100 centimeter cube of dilute hydrochloric acid was used. This can be converted into decimeter cube by dividing by 1000. So it comes equal to 0.1 decimeter cube. Now putting this value in the concentration formula, the number of moles are 0.0392 and the volume in decimeter cube is 0.1 dm cube. Now it comes equal to 0.392 mole per decimeter cube. So we can write 0.392 moles per decimeter cube as the answer. Thank you for watching. Don't forget to like, subscribe and share. Stay tuned for more upcoming videos. Stay happy. Take care.